You take ticket A127. The person after you takes P004. They get called in 4 minutes. You wait 23 minutes. Same bank, same time, different algorithm. You've been there, standing in a bank, holding your ticket, watching the display. Someone who arrived after you get called first. You assumed it was random, or maybe a mistake. It wasn't. Here's the invisible system that decides your turn in line. You walk into a bank. Monday morning, 10:47 a.m. You press a button on the ticket machine. It prints a 127. You sit down. 3 minutes later, someone walks in, presses the same machine, gets P004. You watch the display. Now serving P004 at window 3. For minutes, they arrived after you, got served before you. You look at your ticket, a 127, still waiting. Here's what you assumed. First come, first served. That's how lines work, right? But here's what actually happened. The moment you press that button, the system categorized you, analyzed 12 variables, predicted how long your transaction would take, calculated which window should serve you, and decided that 8 other people waiting would benefit more from being served before you than you would suffer from waiting. You didn't choose a line. You didn't make a decision. The algorithm made it for you. This is the invisible queue management system. It processes 840 people per hour in an average bank, makes 51 decisions per second about who goes where, and optimizes not for individual speed, but for collective efficiency. And here's the strange part. It's mathematically better than any choice you could make yourself, but it feels worse. Before queue management systems, banks had multiple physical lines. 1 line per teller window. You'd walk in, see 6 windows, 6 lines. You'd look at each line, count the people. 3 people in line 1, 3 people in line 2. They look equal. You pick line 1. What you couldn't see. Line 1 had 3 complex transactions. Opening an account, applying for a mortgage, disputing a charge, each taking 15 to 20 minutes. Line 2 had 3 simple transactions. Cash a check, make a deposit, withdraw $200, each taking 90 seconds. You just chose 45 minutes of waiting instead of 4 minutes and 30 seconds. And you had no way to know. This was the problem. In 1985, Bank of America studied their branches in California. Average wait time with multiple lines, 14 minutes and 22 seconds. But here's the disturbing part. While the average was 14 minutes, 23% of customers waited over 30 minutes. And during that same period, teller windows sat empty 18% of the time because their specific line had run out. The math was brutal. 6 windows, each with its own line. You had a 16.7% chance of choosing the optimal line, an 83.3% chance of choosing suboptimal, and a 12% chance of choosing the worst possible line, the one with the person opening a business account who brought incomplete paperwork. Humans are terrible at predicting transaction time. We see 3 people and assume 3 similar transactions. We're wrong 73% of the time. In 1987, Citibank in New York ran an experiment. They installed cameras to track customer behavior. What they found: customers spent an average of 8 seconds choosing a line. In those 8 seconds, they counted people. That's it. They didn't account for transaction type, time of day, teller experience. Nothing. The result: customers chose wrong more often than if they'd chosen randomly. This is the problem the queue algorithm was built to solve. But how? The queue management system doesn't improvise. It follows 3 fundamental rules. The moment you press a button on that ticket machine, you're not just getting a number. You're being categorized. Most systems have 4 main categories. Category A, general service. Withdrawals, deposits, basic inquiries. 68% of customers fall here. Category P, priority. Elderly, pregnant women, disabled individuals, parents with infants. 18% of customers. Category B, business. Commercial accounts, high-volume transactions. 9% of customers. Category question, quick service. Envelope deposits only, ATM assistance. 5% of customers. Each letter goes into a separate virtual queue with different rules. Here's what most people don't know. Some ticket machines have multiple buttons. General Service. Open account. Loan services. When you press General Service, the system assumes a 3-minute transaction. When you press Open account, it assumes 18 minutes. If you press the wrong button, the system's prediction breaks. Your 3-minute transaction estimate turns into 18 minutes of reality. That's when you hear frustrated sighs from people behind you in the virtual queue. In the United States, the Americans with Disabilities Act requires accommodations for people with disabilities. In the UK, the Equality Act 2010 mandates the same. In Canada, similar provincial laws apply. The system enforces this mathematically. For every 3 Category A tickets called, 1 Category P must be served. That's a 3-to-1 ratio. P004 arrived at 10:50 a.m. You, a 127, arrived at 10:47 a.m. P004 gets called at 10:54 a.m. You get called at 11:10 a.m. Is it fair? Legally, yes. The law says priority customers must be accommodated. Morally? Depends who you ask. But here's the nuance. If there are no P tickets in the queue, the system doesn't wait. It calls the tickets continuously. The 3-to-1 ratio only applies when both queues have people waiting. The system learns from historical data. Every transaction that happens feeds the algorithm. Average transaction times at Wells Fargo, according to a 2023 internal study. Envelope deposit, 41 seconds. Simple withdrawal, 1 minute 18 seconds. Check cashing with ID verification, 2 minutes 34 seconds. Account opening, 19 minutes 12 seconds. Mortgage inquiry, 24 minutes 47 seconds. When you take ticket A127 for General Service, the system doesn't know exactly what you'll do. But it knows that 68% of General Service customers do withdrawals or deposits. It predicts probably 90 seconds. When A128 behind you selects Open Account, the system predicts probably 19 minutes. And here's where it gets smart. The algorithm doesn't just serve you an order. It calculates. If I serve a 128's 19-minute transaction now, a 127 through a 135 all wait an extra 19 minutes. That's 9 people times 19 minutes equals 171 minutes of collective waiting. But if I serve a 127's 90-second transaction first, only a 128 waits an extra 90 seconds. The math favors speed. Shorter transactions get priority even if they arrived later, when it reduces total wait time for everyone. This is how P004 got served before you. Not just because of legal priority, because the system calculated that serving them faster reduced collective suffering. And these 3 rules process 840 decisions per day per branch. But rules are just instructions. To execute them across hundreds of customers simultaneously, the system needs infrastructure. There's no choosing a line anymore. There's one invisible line managed by software. When you take ticket A127, you don't join a physical line behind a specific window. You join a virtual queue. Every ticket enters QA. Every P ticket enters QP. Every B ticket enters QB. A central system manages all of them. When a teller finishes with a customer and presses Next on their terminal, the system decides which ticket to call. Not the teller, the algorithm. The benefit: it's impossible to choose the wrong line because there is no choice. The system optimizes for you. TD Bank in Toronto studied this in 2019. Before single queue systems, average wait time was 12 minutes 40 seconds. After implementation, 4 minutes 10 seconds. That's a 67% reduction. Why? Because no teller window sits idle while customers wait. The moment a window is free, the system assigns the next optimal customer. The algorithm behind this is a modified version of shortest job first scheduling used in computer science. Here's how it works in real time. When window 3 becomes available, the system scans all waiting tickets. It estimates transaction time for each. Checks constraints. Window 5 only handles business accounts. Window 2 does everything. Calculates impact. If I call a 127 now, how many people wait how long? Then selects the ticket that minimizes total collective wait time. Real example from HSBC in London, 2022 data. Window 2 becomes free at 11:23 a.m. Queue contains A084, a withdrawal estimated at 1 minute 20 seconds. A 085, account opening, estimated 18 minutes 30 seconds. A 086, deposit, estimated 45 seconds. System could call A084 the oldest ticket in queue. Instead, it calls A086. Why? Because serving A086 45-second transaction frees the window quickly. Then A084 gets served 1 minute 20 seconds. Then A085 18 minutes 30 seconds. If systems serve in strict order, A084 waits 0, A085 waits 120, A086 waits 1950. Total wait 21 minutes 10 seconds. With optimized order, A086 waits 0, A084 waits 45 seconds, A085 waits 205. Total wait 2 minutes 50 seconds. Savings 18 minutes 20 seconds of collective waiting eliminated by changing order. The system makes this calculation 51 times per second across all waiting customers. Modern systems add another layer: environmental awareness. Chase Bank branches in Manhattan installed systems in 2021 that include infrared sensors counting people in the waiting area, cameras, privacy compliant, estimating age demographics to predict P versus A ratio, machine learning models predicting demand. Monday 10 a.m. equals high P volume, retirees. Friday 5 p.m. equals high A volume, workers after shift. The AI predicts demand 15 minutes ahead with 87% accuracy. What this means, at 10:45 a.m., the system detects 23 people in the waiting area and predicts 14 more will arrive in the next 15 minutes based on historical patterns for Monday morning in March. It automatically signals the branch manager, open window 6. By the time those 14 people arrive, an extra window is already staffed. The scale of this: an average bank branch processes 840 people per day over 12 hours. That's 70 people per hour, 1.17 people per minute. The system makes a distribution decision every 38 seconds on average. That's 1,260 decisions per day per branch. Across Bank of America's 3,900 branches in the U.S., that's 4,914,000 decisions per day. In real time, optimizing not for your individual speed, but for collective efficiency. But infrastructure isn't perfect. Sensors fail. Predictions are wrong. And when they do, 3 layers of redundancy activate. Branch managers can override the algorithm. Customer with special need not detected by system. Medical emergency. Person feeling unwell in waiting area. Complain about excessive wait despite optimal algorithm. This happens in 2.3% of transactions. At Wells Fargo, managers have a priority override button on their terminal. One press, and they can manually call any ticket immediately, bypassing the algorithm entirely. It's used sparingly, because every manual override breaks the optimization. That one person you manually serve ahead of schedule creates a ripple. For other people now wait longer than the algorithm predicted. If Category A wait time exceeds 25 minutes while Category P averages 5 minutes, the system breaks its own 3:1 rule temporarily. It shifts to 5:1, 5A tickets for every 1P ticket. Why? Because beyond 25 minutes, customer abandonment spikes. People leave. They don't come back that day. The bank loses the transaction entirely. Studies show wait time perception is nonlinear. First 10 minutes feel like 10 minutes. Minutes 10 to 20 feel like 15 minutes. After 20 minutes, every minute feels like 2. The system knows this. It has a hard limit. No ticket waits more than 25 minutes unless absolutely unavoidable. March 15th, 2021. Barclays Bank, Birmingham, UK. Software update deployed at 9:47 a.m. Bug in the code. System misclassified 52 Category A tickets as Category P. Result: 52 people received priority treatment they weren't entitled to. Actual priority customers, Category P, waited an average of 31 minutes instead of their usual 6 minutes. Complaints: 89 filed that day versus average of 2 per day. The branch manager noticed the pattern at 11:20 a.m. when an elderly woman, clearly Category P, complained about waiting 40 minutes. Manager checked the system logs, saw the anomaly, called IT support. Fixed time: 2 hours 18 minutes to identify the bug, write a patch, deploy, and restart all terminals. During those 2 hours, the branch reverted to manual queue management. Tellers called tickets in strict numerical order, ignoring categories entirely. Wait times during manual operation: 19 minutes average versus 4 minutes with algorithm. Compensation: Barclays offered fee waivers for affected customers and published an internal report. The bug was caused by a Boolean logic error. The system checked if not category instead of if Category P. Every non-A ticket became P, including B, business, and Q, quick service. After the fix, the system added a failsafe. If more than 15% of tickets in any hour are classified as P, trigger an alert. Because statistically, P represents 18% of customers overall, but rarely exceeds 15% in a single hour unless there's a demographic anomaly, like a senior center nearby, or a system error. The system predicts transaction time with 87% accuracy. That means 13% of transactions take longer than estimated. Why? Customer discovers a problem mid-transaction, requests additional service, brings incomplete documentation, asks questions that extend the interaction. One transaction predicted at 2 minutes takes 14 minutes. That delays the next 12 tickets in queue by 12 minutes each. Cascading effect. There's no redundancy for this. The system adapts in real time, recalculating wait times and distributions as new data comes in. But it can't prevent the initial disruption. This is the 13% the algorithm can't solve. Human unpredictability. But even with these failures, the system works 87% of the time. And that affects you directly every time you take a ticket. Now you know how the queue management system works. Here's how it affects you. Illusion of control. You took ticket A127, but you didn't choose which window would serve you. The system chose for you. Your brain experiences it as choice. You pressed a button. You got a ticket. You made a decision. But the only decision you made was go to the bank. Everything after that, which category, which window, when you're called, was determined by an algorithm calculating 23 variables you never saw. And when you wait 23 minutes, your brain blames your choice. In reality, the algorithm calculated that serving you now would delay 8 other people more than making you wait delays you. Your wait isn't random. It's optimized, just not for you individually, for everyone collectively. Psychological phenomenon documented by MIT in 2018. Humans perceive wait time exponentially, not linearly. First 5 minutes feel like 5 minutes. Minutes 5 to 10 feel like 8 minutes. Minutes 10 to 15 feel like 12 minutes. After 15 minutes, every minute feels like 2 minutes. Wait 12 minutes? Feels acceptable. Wait 18 minutes? Feels absurd. Even though it's only 50% more time, it feels 200% worse. The system knows this. That's why the 25-minute hard limit exists. Not because the math says it's optimal, because human psychology says beyond 25 minutes, perceived wait time becomes unbearable and customers abandon the queue. The algorithm optimizes for math, but it's constrained by psychology. Comparative study, Stanford University, 2019. Multiple physical lines, average wait time, 14 minutes 2 seconds. But you see other lines moving faster. High frustration, single virtual queue, average wait time, 4 minutes 10 seconds. But you can't see comparison. Lower frustration. The paradox, single queue is mathematically superior. But psychologically, some people prefer multiple lines because they feel control, even if that control is illusory and makes them wait longer. Some banks experimented with reverting to multiple lines, not for efficiency, For customer satisfaction, Royal Bank of Canada tested this in 2020 across 12 branches. Customer satisfaction surveys showed 18% preferred multiple lines despite waiting 3 times longer, specifically citing feeling like I have a choice. The bank kept single queue systems because actual wait time reduction outweighed perceived preference for control. Those digital displays showing which tickets are being called, they're also collecting data. How often people look at the display indicates anxiety level. How many people abandon queue, take ticket but leave before being called. How long people actually spend at windows versus predicted time. Machine learning models use this data to improve predictions. At TD Bank branches in Vancouver, the system detected a pattern. Tickets taken between 12 o'clock and 12:30 p.m. had 23% higher abandonment rate than other times. Why? Lunch hour. People on lunch break couldn't wait longer than 15 minutes without being late returning to work. The system adapted. During 12 to 12:30 p.m., it automatically prioritizes shorter transactions even more aggressively and opens additional windows if available. Result: abandonment rate dropped to 9%. You never knew you were being observed. The system learned your behavior and adapted silently. But here's what most people get wrong about queue systems. They think arriving early in the day means faster service. It doesn't. Experiment at Chase Bank branches in Chicago, 2022. They tracked 30 days of operation. Customer arriving 10 a.m., opening time. Average wait equals 8 minutes, 34 seconds. Customer arriving 11:30 a.m., peak. Average wait equals 11 minutes, 22 seconds. Customer arriving 3:30 p.m., valley. Average wait equals 3 minutes, 41 seconds. Why? The system adjusts staff dynamically. 10 a.m., 3 windows open. Moderate demand equals moderate wait. 11:30 a.m., 7 windows open. High demand equals longer wait despite more windows. 3:30 p.m., for windows open, very low demand equals minimal wait. Counterintuitive result. Arriving during off-peak is better than arriving early. But the system doesn't advertise valley hours. Because if everyone learned 3:30 p.m. is fastest, everyone would arrive at 3:30 p.m., creating a new peak. The system optimizes, but it doesn't educate, because education would break the optimization. So, to recap, the bank queue algorithm works in 3 layers. First, classification. The moment you press that button, you're categorized. A for general, P for priority, B for business, Q for quick. Each category has different rules, different predicted times, different priority levels. Second, prioritization. Legal requirements mandate P before A in a 3-to-1 ratio. Efficiency rules prioritize shorter transactions when it reduces collective wait time. Your individual position in queue is constantly recalculated based on who else is waiting and what they need. Third, distribution. An algorithm decides which window calls you based on minimizing total wait time for everyone, not just you. Window 3 doesn't call next in line. It calls next optimal ticket based on 23 variables and 840 people processed today. But here's what you probably didn't realize. This same algorithm doesn't just run in banks. It operates in call centers, deciding which customer call goes to which agent. Airports determining which check-in line directs you to which counter. Hospitals triaging which patient sees which doctor. Restaurants where the host decides which server gets which table. Same invisible system, different application. Right now, across the United States, 72,847 bank branches are operating. 1,824,319 people are in queues, physical and virtual. The system makes 51 decisions per second about who serves whom. That's 4,406,400 decisions per day across the U.S. banking system alone. This invisible system solves an ancient philosophical problem. How do you be fair when first come, first served isn't efficient? Answer: you redefine fairness. Not as who arrived first gets served first, but as minimize collective suffering. Your 23-minute wait prevents 8 people from waiting 12 minutes each. That's 96 minutes of suffering avoided at the cost of 11 extra minutes for you. You would have waited 12 minutes anyway in a perfect system. The algorithm added 11 to save 96. The system chooses 11 minutes of individual pain to prevent 96 minutes of collective pain. Every time, without exception. Next time you take ticket A127 and watch P004 get called first, you'll see it differently. Not unfairness. An algorithm calculating 23 variables, predicting 47 transaction times, deciding that collective efficiency matters more than individual chronological order. This is the queue management system. The algorithm you never see, but that decides your turn 51 times per second in 72,847 branches, optimizing for the many while you wait as one.